The quiet universe. The new gravitational wave era. What hundreds of signals are whispering. Some nights, the universe doesn't shine. It hums. A faint vibration passes through space and time, and for a moment, two black holes, or two neutron stars, write a brief signature into the fabric of reality. Tonight, we're going to listen to that signature. This episode is a calm, documentary-style analysis and synthesis of modern gravitational wave astronomy. When we describe visuals, treat them as AI/CGI scientific visualizations or dramatized recreations, not real footage. And when we reach beyond what is firmly established, I'll label it as a hypothesis, a possibility, or an open question. Now let's begin with something solid. Gravitational waves are ripples in space-time, predicted by Einstein's general relativity and directly detected by laser interferometers beginning in 2015. Since then, the field has moved from first detection to routine listening. Each observing run feels less like a single headline and more like a season of weather, a steady stream of events, patterns, and surprises. If you're listening from the outside, that can be hard to feel. News articles focus on the biggest or the weirdest, but the deeper story is quieter. Repeated detections are what transform a discovery into an astronomy. In that spirit, this episode is not about one dramatic event. It's about the era itself, especially the most recent long observing campaign, often called 04. Public alerts during 04 reported on the order of hundreds of candidate signals in near real time. Over time, as data analysis and validation continues, many of those candidates become cataloged detections in published releases. So what is the universe whispering to us through this growing chorus? We'll explore 5 gentle themes. What a gravitational wave signal really is and what detectors actually measure. Why a high event rate matters more than a single spectacular event. What we are learning about black holes and neutron stars as populations, not just individuals. What the data is beginning to test, relativity, matter at nuclear density, and the story of how compact objects form. And what remains uncertain, especially in a world where candidate alerts arrive quickly and careful confirmation arrives later. And we'll do it slowly, like a nighttime walk. A small question to begin. When you imagine listening to the universe, do you picture a loud cosmic roar or a steady, quiet rain of distant mergers? If you'd like, tell me which image feels more true to you in the comments.
Now, let's take the gentlest step. How an interferometer turns a passing ripple in space-time into something we can measure. To make this episode truly restful, I'll avoid rapid-fire facts. Instead, I'll give you a few anchors, simple ideas you can return to, like stones on a path. Anchor 1. Gravitational waves do not carry images. They carry timing. A photon tells you where it came from by arriving along a line. A gravitational wave tells you what happened by how its rhythm changed over time. That rhythm is the story. Anchor 2. The most important discoveries in this field are often not new objects, but new statistics. When detections become common, the universe stops being a collection of anecdotes and becomes a measurable ecology. Anchor 3. Most of what we say tonight will sound confident only because we will keep it inside its proper boundaries. If something is still uncertain, we will say so. If something is a hypothesis, we will label it. That's not caution for its own sake. It's the method that makes future discoveries meaningful. And finally, a gentle promise: no jump scares in language. No phrases like "shocking secret" or "they don't want you to know." That tone doesn't belong in science, and it doesn't belong in sleep. Now take a breath and imagine a quiet laboratory on Earth. Vacuum tubes stretching across the landscape. Mirrors held in steady silence. Those machines are not looking at the sky. They are waiting for space itself to ripple. We'll start with the simplest picture of a waveform. Then we'll let that picture widen, slowly, until it becomes an entire era of listening. And if you ever feel lost in the jargon, return to one gentle sentence. A gravitational wave is a change in distance that repeats like a slow breath. That's all you need to hold for now. Everything else is detail built around that calm core. Now, let's continue. Before we move on, a tiny pause for you. If your thoughts wander, let them. This episode is built so that you can drift in and out and still return to the main thread. Now, gently, into the first technical layer. At first glance, LIGO, Virgo, and Kagra seem almost impossibly delicate for cosmic work. They do not look like telescopes. They look like long, quiet hallways of light. A laser is split into two perpendicular arms. The light bounces back and forth between mirrors, and if space-time stretches a tiny bit along one arm while squeezing along the other, the returning light recombines with a slightly different phase. That phase difference produces an interference pattern, and instruments whisper that something passed through. The key is scale. Gravitational waves distort distances by an incredibly small fraction. The change in length is smaller than an atomic nucleus over kilometers of arm length. So detectors must be extremely stable, highly isolated, and continuously monitored. And this is why the signal is not a photo, it's a time series, strain versus time, a waveform. If we slow that waveform down into the audible range, it can sound like a chirp, a rising tone as two objects spiral together faster and faster. But in the real data, it is not a clean chirp sitting alone in silence. It is buried in noise, seismic vibrations, thermal fluctuations, tiny instrumental couplings, and countless subtle disturbances. So detection is a statistical act. Analysts run matched filter searches using banks of waveform templates. They look for patterns that rise above the noise with high confidence. They cross-check between detectors. They perform data quality vetting. And only after layers of validation do events appear in catalogs with measured parameters and uncertainties. That's why you may hear two kinds of language:
candidate events or public alerts, which arrive quickly to enable follow-up astronomy, and confirmed detections in published catalogs, which arrive later with the full weight of analysis. Both are valuable, but they serve different purposes. Now, what changed as the field matured? In early years, a single detection felt rare. It was a jewel. But as sensitivity improves, the universe becomes louder. Not because it changed, because we did. Our instruments reached farther. The volume we sample grows dramatically with range. If you double the distance reach, you sample about 8 times the volume. So an incremental improvement in sensitivity can create a large jump in event rate. This is why hundreds of signals is not just a brag, it is a shift of regime. It means we can stop asking only, does this exist, and start asking, what does the distribution look like? And distributions are where the deep astrophysics lives. Before we go there, let's add one calming detail. Even though these detectors are extraordinary, they are still earthly machines. They have maintenance breaks. They have commissioning phases. They have evolving sensitivity. And networks matter. The more detectors observe simultaneously, the better we can localize a signal on the sky. So when you hear about an observing run, imagine not only a single instrument, but a global network trying to stay in sync. Like multiple ears listening for the same faint vibration. If you'd like an engagement question here, would you rather hear fewer events described in detail, or many events described as a broader, calmer pattern? Tell me in the comments. This channel can do either, depending on what helps you rest. Now, with the measurement picture in mind, let's talk about the main characters of the gravitational wave sky: black holes and neutron stars. One way to make the idea intuitive is to imagine a ruler drawn on space-time itself. If a gravitational wave passes, the ruler does not simply move. The scale of distance changes and then changes back. It is an oscillation of geometry. In an interferometer, that oscillation becomes a difference in phase between two laser beams, and the phase difference becomes a record. But the record has complications because the detector is never perfectly quiet. Some noise is low frequency, ground motion, wind, microseisms from ocean waves. Some noise is high frequency, quantum shot noise in the laser, thermal motion in materials, subtle resonances in the instrument. And some noise is not noise in the usual sense, but glitches, short disturbances that can mimic a real signal if you look only briefly. So the community learned to do two things at once: listen fast and verify carefully. That's why public alerts exist. They allow a rapid response when a candidate might have an electromagnetic counterpart. But the more formal publications take time, because the waveform must be tested against data quality, instrumental artifacts, and statistical false alarm estimates. If you ever see a retraction, it is not an embarrassment. It is a sign that the system works. It corrects itself. Now, what does signal-to-noise ratio mean in this context? It is not a volume knob. It is more like confidence that a pattern matches a physically meaningful template better than random noise can. A strong event can be visible even in a quick look at the strain data. A weak event may require careful filtering to become apparent. And because event counts include many weak events, the era of hundreds of signals is also the era of subtle statistical listening. This is why you can think of O4 as a maturity test. O4 was designed not only to catch events, but to operate a pipeline: detect, alert, classify, and later confirm. In late 2025, public statements about O4 described it as the richest run so far in the advanced detector era, with roughly a few hundred candidate signals identified in near real time. That alone tells you how far the field has come since 2015, when each detection was a once-in-a-while surprise. Now, with the measurement machinery in mind, we can talk about what these signals are saying, quietly, about the lives and deaths of massive stars. In gravitational wave astronomy, the most common story begins with a pair. Two compact objects, often black holes, locked in a long, slow dance. They orbit each other for millions to billions of years, shedding energy through gravitational waves. The orbit shrinks, the frequency rises. Then, in the final seconds, the dance accelerates into a rapid spiral and merger. The signal we detect is usually dominated by three phases: inspiral, merger, and ringdown. The inspiral phase is the clearest place to measure masses and sometimes spins. The merger and ringdown carry information about the final black hole and provide a stage for testing general relativity in the strong field regime. Now, here is the quiet power of having many signals. With one event, you can say, "This happened." With dozens or hundreds, you can say, "This happens in a pattern." You can infer how black hole masses are distributed, how often black holes form in pairs, what their spins tend to be, and whether their orbits are typically circular or sometimes eccentric. You can also compare the population to formation scenarios. Some black holes likely form and merge inside isolated binary star systems. Two massive stars evolve, collapse, and remain bound. Others may form and merge dynamically in dense environments: globular clusters, nuclear star clusters, or the disks of active galaxies. These channels can leave statistical fingerprints: different spin alignments, different mass distributions, different eccentricity expectations, and different merger rate evolution with cosmic time. Now, in a calm voice, you can think of it like this. A single footprint tells you something stepped here. A trail of footprints tells you how it walked. Now, a detail that often surprises new listeners: gravitational waves measure red-shifted masses. If a merger is far away, cosmic expansion stretches the waveform and makes the masses appear larger in the detector frame. To infer the source frame masses, we need distance, and distance estimates carry uncertainty. So whenever you hear precise mass numbers, remember they come with statistical spreads. This is normal. It's part of the language of inference. Now, what about neutron stars? Neutron star mergers are rarer in the catalogs so far than black hole mergers, but they are especially valuable because they can be multi-messenger. If the merger produces electromagnetic radiation, gamma rays, optical kilonova light, or radio afterglows, then telescopes can pinpoint the host galaxy. That yields a redshift and distance and can turn a gravitational wave event into a precision probe. And even without light, neutron stars can imprint subtle effects in the waveform through tidal deformability, how easily each star is stretched by its companion's gravity. Those tidal effects, if measured well, can constrain the equation of state of ultra-dense matter. In other words, gravitational waves can help us learn what matter does at densities beyond what we can reproduce in laboratories. That's a quietly profound idea. Now, 04 era public alerts included many black hole candidates and a smaller number of neutron star involving candidates. It's important to treat the candidate label seriously. The classification is probabilistic and it can be updated as analysis improves. So rather than treat every alert as a finalized portrait, we'll use them as a window into the era, a time when detections are frequent enough that we can talk about the sky as a living population. If you'd like an engagement question, do you find it more interesting to learn about individual exotic events or to learn what the whole population implies about how the universe builds compact objects? Comment below. Your preference can shape the balance of future episodes. Now, we'll shift to the next quiet theme, localization and what it means to point a gravitational wave detection at the sky. A common misunderstanding is that every gravitational wave detection is the same kind of thing. In reality, each detection is a different point in a huge landscape. Different masses, different spins, different distances, different orientations, different environments. And because the waveform is sensitive to these features, the catalog becomes a map. Here is a calm way to read that map. Mass tells you how heavy the system is and how fast it evolves. Heavier black holes merge at lower frequencies, and their signals can be shorter in time for ground-based detectors. Lighter systems spend longer in the detector band, giving more in-spiral cycles and sometimes more detailed parameter inference. Spin tells you something about formation. Aligned spins can hint at a shared evolutionary history in an isolated binary. Randomly oriented spins can hint at dynamical assembly in crowded environments. This is not a perfect rule, it is a statistical tendency. Then there is mass ratio. How unequal the masses are also carries formation clues. Highly unequal mass ratios can be harder to create in some channels, easier in others. Again, statistical, not absolute. Then there is eccentricity. Most binaries radiate away eccentricity long before reaching detector frequencies, so circular inspirals are expected from many systems. But certain formation pathways, like dynamical capture, can produce measurable eccentricity. So searches for eccentricity are searches for rare formation histories. Now, one more subtle point. Detectors do not measure distance directly the way a radar does. Distance is inferred from amplitude, but amplitude is entangled with orientation. A face-on system can look louder than an edge-on one at the same distance. So distance estimates naturally carry uncertainty. This is why catalogs are probability distributions, not single numbers. And it's why the phrase "consistent with" appears so often in published work. In a calm documentary, that language is not hedging, it is precision. Now, take a moment to feel the bigger idea. Every detection is a death, two compact objects losing their last orbit and merging. But it is also a birth of a new black hole, newly formed, newly spinning, newly ringing down. And in the statistics of many births, the universe reveals how it makes its darkest objects. If you want a sleep-friendly visualization, imagine a long hallway of distant mergers, each one a soft pulse. The pulses are not identical. Some are low and heavy, some are higher and lighter. Some are short, some stretch longer. Over time, the pattern becomes familiar, and familiarity becomes knowledge. Now we can step from what a signal is to where it is, and why a network transforms a pulse into a location on the sky. A gravitational wave detector is not a camera, it is a listener. And a single listener does not know direction well. It hears a wave, but the wave could have come from many parts of the sky. Localization improves when multiple detectors hear the same signal. Differences in arrival time, sometimes milliseconds, help triangulate. Differences in detector orientation help constrain polarization. Together, a network can narrow the source to a patch of sky. Sometimes that patch is small enough to search with telescopes. Sometimes it is large, like a broad crescent across the sky. The size depends on signal strength, network size, and detector sensitivity at that moment. This is why the network matters. When more detectors are operating simultaneously, localization tends to improve. When fewer are operating, localization often degrades. So a long observing run naturally includes a mix, periods with sharp sky maps and periods with wide uncertainty. Now, why does localization matter? Because the most transformative science comes when we connect waves to light. If a neutron star merger produces a gamma-ray burst and a kilonova, a well-localized gravitational wave alert allows telescopes to catch the transient quickly. That's how we learn where it happened, what galaxy hosted it, and what elements were forged in the aftermath. Even for black hole mergers where electromagnetic counterparts are not guaranteed, localization enables searches for rare scenarios, mergers inside gas-rich environments, possible weak flares, or neutrino coincidences. Most of the time, the universe stays dark in electromagnetic light for black hole mergers, but most of the time is a statistical statement, and statistics improve with many events. Now, let's talk about public alerts, because they're part of the 04 experience. During 04, public alert systems frequently issued rapid notices for candidate events, including preliminary classifications and sky maps. These alerts are meant for rapid response. They're intentionally fast. They are updated or retracted if later analysis suggests the candidate was not astrophysical. This is an integrity point worth stating clearly. A retraction is not a scandal. It is part of honest scientific operations. When you choose speed, you accept that some alerts will be revised. So a calm channel does not treat preliminary alerts as final truth. It treats them as a message that a wave-like pattern may have occurred with a probability that will be refined. That is the proper posture. Now, if you do visual storytelling for this episode, you can illustrate localization in a sleep-friendly way. A glowing patch on a sky dome, slowly shrinking as more detectors join, then widening again during periods of reduced network uptime. These visuals can be abstract, and they should be labeled as visualization in the description if needed. Now, with localization understood, we can touch a deeper question. What is hundreds of signals actually doing for science? It is shifting the field from discovery to demographics. In the next file, we'll talk about population inference, how scientists use many detections to estimate merger rates, mass distributions, and formation channels. And we'll keep it gentle, no equations, just the logic of careful counting. Engagement question: when you hear statistics, does it feel cold? Or does it feel like a way of turning many small whispers into one clearer story? If you'd like, tell me in the comments. Now, let's move into the quiet power of populations. There's also a beautiful geometric reason localization improves with networks. A wave reaches different detectors at slightly different times. That time delay corresponds to a ring on the sky, all directions that produce that delay. With 2 detectors, you often get a broad ring. With 3, those rings intersect and narrow. With more, the patch can shrink dramatically. But even with multiple detectors, localization is rarely a single dot. It is a probability map because noise and waveform degeneracies blur the inference. So the sky map is not a pinpoint, it is a where the wave probably came from region. If you want to connect this to the real rhythm of observing runs, networks also have seasons inside seasons. A detector might go offline briefly. Commissioning work might improve sensitivity. A maintenance window might pause observations. In early 2025, for example, public schedules described a planned break for maintenance and commissioning during 04 and extensions to the runtime line. These operational details matter because they determine how often the network has 3 years listening versus 1 or 2. For multi-messenger astronomy, those differences can be crucial. Now, here is a calm truth. The gravitational wave sky is already full, but our ability to see it in light depends on coincidence and readiness. Coincidence is the event of a type likely to produce light. Is it close enough? Is it oriented favorably? Readiness: are telescopes watching? Are alerts fast? Is localization tight enough to search? So the larger story of 04 is partly sociological, in a good way. It is a global coordination story. Detectors issue alerts, astronomers respond, data is shared, and the community learns which strategies work. This is why the field can feel like it is accelerating, not only because the instruments improve, but because the entire ecosystem improves. Now, a quiet engagement question. When you imagine a cosmic event, do you feel more drawn to the idea of pinpointing it on the sky, or to the idea of learning the statistics of many events without ever knowing their exact host galaxy? Both are valid forms of knowing. Tell me which one you prefer. Next, we'll deepen the population story and make it feel concrete. How does a catalog become a claim about the universe? Once you have many detections, a new kind of astronomy begins. Instead of focusing only on what happened in a single event, you ask, how often does this happen? What kinds of systems dominate? What kinds are rare? What does the distribution say about the life cycles of stars? This is population inference. In practice, it's careful accounting with uncertainty. You start with a catalog of detections and candidate classifications. You correct for selection effects, the fact that detectors are more likely to find loud events than quiet ones, near events than far ones, higher mass mergers than lower mass mergers, depending on frequency bands and sensitivity. This correction is essential. Without it, the observed population would be biased. So you build models for the distribution of masses, for the distribution of spins, for the merger rate as a function of redshift, and for how those features might evolve over cosmic time. Then you ask which models best explain the data. This process yields results like a typical range of black hole masses seen in mergers, a typical preference for low or moderate spins in many events, and hints about whether spin directions are aligned or randomly oriented. But every one of these statements carries uncertainty and modeling choices. So in an integrity-first channel, we keep the language measured. The data suggests, the population favors, within uncertainties, depending on priors and selection modeling. Now, what has been especially interesting in the gravitational wave era is the variety of masses. Some events involve black holes around a few tens of solar masses. Some appear heavier. Some may involve objects in the so-called mass gap regions that were once thought less likely, though the boundaries of such gaps depend on astrophysical modeling and remain an active area of study. The important point is not to treat any one boundary as absolute. It is to notice that gravitational wave catalogs are reshaping our intuition about what stellar remnants can look like. And once again, many events matter. A single heavy merger could be a fluke. A pattern of heavy mergers could imply low metallicity star formation environments, hierarchical mergers where black holes merge and then merge again, or other channels that build mass through repeated interactions. Now let's talk about rates. Rates tell us how common compact binaries are and how they evolve. They also feed into broader cosmology, how often certain kinds of explosions happen, how much gravitational wave energy is injected into the universe over time, and what future detectors might observe. Rate estimates are sensitive to detector sensitivity, observing time, and selection modeling, so they update as catalogs grow. This is why an observing run like 04 matters even beyond individual discoveries. A long run with many candidate events can provide a stronger statistical anchor for rates once the final vetted catalogs are produced. Now, there is also a quieter kind of science, the search for rare categories. For example, binary neutron star mergers, neutron star black hole mergers, events with unusual mass ratios, or hints of eccentricity. Rarity is hard to prove with a handful of detections, but with hundreds, you can begin to bound how rare something is. So many events does not just create averages, it creates the possibility of mapping tails. Now, a gentle engagement question. Do you like hearing about the average, or do you prefer the rare outliers as long as we label uncertainty clearly? Comment below. Your preference helps shape future episodes. Next, we'll step into one of the most subtle and beautiful uses of gravitational waves itself, testing gravity itself. We will do it calmly with careful language. Let's continue. The phrase selection effect can sound abstract, so here is a gentle example. Imagine you are listening for whispers in a room. You will notice loud whispers more often than soft ones. If you tried to infer how often people whisper using only what you heard, you would underestimate the quiet whispers. Gravitational wave detectors face the same problem. They detect the loudest, clearest events most easily. Loudness depends on distance, mass, orientation, and how well the waveform sits inside the sensitive frequency band. So, to infer the true population, scientists must model what they could have detected. This is usually done through injection studies, simulated signals added to real data to measure detection efficiency. That efficiency becomes part of the inference. This is why when you hear a population result, it is never just counting events. It is counting events with an understanding of what you missed. Now, what does the population inference produce? It produces posterior distributions over population parameters, not a single number, but a range. For example, a range for the merger rate per cubic gigaparsec per year, a range for typical masses, a range for how spins are distributed. And with enough events, you can detect subtle features, a pileup, a cutoff, a mixture of subpopulations. These features can speak to stellar evolution. Metallicity matters because metal-poor massive stars lose less mass in winds, which can yield heavier black holes. So, if the catalog favors heavier black holes, it may hint at contributions from low metallicity environments. But this is not a simple one-to-one mapping. It becomes a multi-parameter inference problem. And this is where the calm discipline of the field shows. Researchers do not usually claim a single formation channel. They often infer a mixture. In other words, the universe is not obligated to pick one recipe. It can cook with many. Now, one more important ingredient: hierarchical mergers. In dense environments, a black hole formed by a previous merger can merge again. This can build heavier black holes and can change spin distributions. It can also create distinctive mass ratios. But detecting hierarchical patterns requires enough events to see beyond randomness. So again, many events matter. O4, described as yielding roughly a few hundred candidate events in real time, represents a statistical leap. Even though final catalogs arrive later, the scale alone suggests stronger population constraints are coming, because each additional observing month adds both events and calibration experience. Now let's keep our integrity rule. If you see a headline that says O4 proves black holes form this one way, that's almost certainly too strong. What O4 can do is tighten the probability landscape of formation scenarios and highlight which models are becoming less plausible. That's powerful, and that's scientific. Next, we'll turn back to the most fundamental question. What does this catalog say about gravity itself, and how careful do we need to be before we claim a deviation?
General relativity has passed many tests in the solar system and in astrophysical settings. But gravitational waves allow something special. Tests in the strong field, highly dynamical regime. Two black holes merging is not a gentle perturbation. It is a storm in spacetime, and the waveform encodes whether the storm behaves as Einstein predicted. So, what do scientists test? They compare observed waveforms to predictions from general relativity. They look for deviations,
in the phase evolution, the relation between in-spiral and merger, the ring-down frequencies of the final black hole, and the consistency of parameters inferred from different parts of the signal. They also test ideas like whether gravitational waves travel at the same speed as light, whether they disperse in frequency-dependent ways, and whether extra polarization modes might exist. Most results so far are consistent with general relativity within current uncertainties. That statement is important. It is also not the end of the story, because uncertainty shrinks as catalogs grow. Many weak signals, combined statistically, can test subtle deviations that no single event can constrain. This is another reason hundreds of events matters. Now, there's a boundary between what's established and what's speculative. It is established that current published tests show no compelling evidence of departures from general relativity in the observed compact binary signals to date. It is speculative to claim that any single unusual event breaks relativity. That kind of claim requires careful modeling and strong evidence. So in this channel, we will not treat gravity tests as drama. We will treat them as careful consistency checks. Now, another subtle test comes from the final black hole itself. After merger, the remnant black hole rings down like a bell. General relativity predicts that the frequencies and damping times of that ring down depend only on the remnant's mass and spin. So, in principle, if you can measure multiple ring down modes, you can test the no-hair theorem. In practice, measuring multiple modes is difficult with current detectors, but the goal becomes more achievable as sensitivity improves and as louder events accumulate. So the message is gentle. We are not fully there yet, but we are walking toward it. Now, gravitational waves also test astrophysical environments indirectly. For example, if mergers often occur in gas-rich environments, the waveform could show subtle imprints of orbital evolution or eccentricity. So far, most detected systems are consistent with nearly circular in spirals, but the search for eccentricity continues. Again, many events matter. Now, if you are still listening, here is an engagement question. Do you find testing Einstein relaxing in a strange way, or does it feel too technical for sleep content? Comment below. I can keep this section more meditative or more detailed depending on what you prefer. Next, we'll shift to neutron stars and the quiet question of matter at nuclear density. What gravitational waves can tell us about the inside of a star that is basically a giant atomic nucleus? Let's continue. Here is a useful way to understand gravity tests. They are mostly tests of consistency. General relativity predicts a very specific relationship between the way the orbit evolves during in-spiral and the properties of the remnant black hole during ring-down. So a classic test is to infer parameters from the in-spiral and compare them to parameters inferred from the post-in-spiral part. If they agree within uncertainties, that supports the model. Another class of tests looks for parameterized deviations, small changes in the waveform phase at different orders. Researchers ask whether the data prefers those deviations. So far, across published catalogs, the answer is generally no compelling preference. But even no preference is information. It produces constraints. Constraints rule out large classes of alternative models. Now, why not declare Einstein is proven forever? Because science does not work that way. Constraints improve, instruments change, new regimes become accessible, and some theories can mimic Einstein in one regime while differing in another. So the honest stance is general relativity remains consistent with current data, and the tests continue. Now, if a deviation were ever found, it would have to clear multiple hurdles. It would need to appear consistently across independent analyses. It would need to survive careful modeling of detector systematics. It would need to be robust to assumptions about source populations. And it would need to be compatible with other constraints, like electromagnetic observations and solar system tests. That is a high bar, and it should be. This is why the hundreds of events era is so important. It raises the statistical bar for claims and strengthens the field's ability to do cross-checks. Now, a calmer, more personal thought. Some listeners find it soothing that Einstein's equations still hold up under such violent cosmic conditions. It feels like stability in the laws. Others find it exciting that the tests are still open, that the universe might one day show us a crack. That feels like mystery. Both reactions are human. The science does not require you to pick one. It only requires you to keep the language accurate. Now, as we move to neutron stars, keep a simple image. Black hole signals are often clean tests of gravity. Neutron star signals are often clean tests of matter. Two kinds of physics, both carried by waves. Let's step into the interior of neutron stars, quietly. Neutron stars are among the strangest objects in physics. They are compact remnants of massive stars. They pack more mass than the sun into a sphere roughly the size of a city. Inside them, matter is crushed into forms we can only model, not reproduce. So how can gravitational waves help? Through tides. As two neutron stars orbit, each star's gravity raises tidal bulges on the other. Those tides alter the orbital motion slightly. That alteration imprints a small, measurable change in the gravitational wave phase. From that phase shift, scientists can infer tidal deformability, how squishy the neutron star is. A stiffer equation of state produces smaller deformability. A softer one produces larger deformability. This is a quiet miracle. We can learn about subatomic physics by listening to a cosmic binary. Now the catch is sensitivity. Tidal effects are subtle. They are easiest to measure in nearby events, high signal-to-noise detections, and events where the in-spiral signal is long enough in band. So as detectors improve, neutron star science becomes richer. This is why a long observing run matters even when black hole mergers dominate the counts. You might have dozens of black hole mergers for every neutron star event, but each neutron star event carries unique nuclear physics value. And if a neutron star merger is seen in light, the value multiplies. A kilonova can reveal our process element synthesis. A gamma-ray burst can reveal jets. A host galaxy identification can give distance redshift pairing, enabling cosmological measurements like the Hubble constant using standard sirens. Now, we must keep the integrity line. Not every candidate binary neutron star classification is correct. Classifications are probabilistic. Many candidates eventually are refined, and the most careful conclusions come from vetted catalogs and well-studied multi-messenger cases. So, in a sleep-friendly documentary, we speak in the conditional, can, may, in principle, if observed. Now, there's another frontier, neutron star black hole mergers. These systems test tidal disruption in a different regime. If the neutron star is torn apart before it crosses the black hole's horizon, it might produce electromagnetic emission. If it plunges intact, it might be dark. Whether disruption occurs depends on the mass ratio, the black hole spin, and the neutron star's equation of state. So each detection is a piece of a parameter space puzzle. And again, many events matter. With enough detections, you can begin to map which combinations lead to light, which lead to darkness, and what that implies about the interior of neutron stars and the spins of black holes. Neutron stars are among the strangest objects in physics. They are compact remnants of massive stars. They pack more mass than the sun into a sphere roughly the size of a city. Inside them, matter is crushed into forms we can only model, not reproduce. So how can gravitational waves help? Through tides. As two neutron stars orbit, each star's gravity raises tidal bulges on the other. Those tides alter the orbital motion slightly. That alteration imprints a small, measurable change in the gravitational wave phase. From that phase shift, scientists can infer tidal deformability, how squishy the neutron star is. Now, an engagement question. Would you like future episodes that focus specifically on neutron stars and kilonovae, or do you prefer a broader all gravitational waves overview? Tell me in the comments. Next, we'll talk about something even quieter than individual mergers, backgrounds and continuous signals. The idea that the universe may have a persistent gravitational wave hiss. Let's continue slowly. There is also a poetic irony here. Neutron stars are silent in an optical sense for most of their lives. They can be dim, distant points. But in gravitational waves, they can speak about their interiors. The tidal signature is a kind of honesty. It cannot be faked by light. It comes from bulk matter responding to gravity. Now, the equation of state is not a single curve everyone agrees on. It is a family of models, constrained by nuclear theory, observations of massive pulsars, X-ray timing and spectroscopy, and now gravitational wave constraints. Each method brings a different kind of evidence. Gravitational waves bring dynamical evidence. And here is where careful phrasing matters. Instead of saying gravitational waves reveal the true equation of state, we say gravitational waves constrain the space of plausible equations of state. That is accurate, and it leaves room for future refinement. Now, a subtle point. Tidal deformability is easier to measure for lighter neutron stars than for heavier ones, because heavier stars tend to be more compact and deform less. So the population of neutron star masses matters, and the number of neutron star detections matters. This is why each additional neutron star event is important, even if black holes dominate the catalog. Now, let's talk about neutron star-black hole mergers again, because they can be visually compelling if you choose to illustrate them. A disruption scenario might be shown as a glowing debris stream spiraling into a black hole. A non-disruption scenario might be shown as a clean plunge. But remember, these are visualizations, not footage. And whether disruption occurs is a conditional statement based on parameters. So the honest narration uses may and can and depending on. Now, why does all this matter beyond curiosity? Because neutron star physics connects to element formation. Kilinovae can produce heavy elements like gold and platinum through rapid neutron capture. So neutron star mergers are not just fireworks, they are chemical factories. But the degree to which they dominate cosmic heavy element production remains debated and depends on rates, yields, and galaxy evolution. So again, careful language. Now, a calming engagement question. When you hear gold may come from neutron star mergers, does it make the universe feel more intimate, like everyday materials are connected to cosmic events? If you want, leave a comment with the object near you you'd like to imagine as cosmic for even a moment. Next, we'll shift to the quietest listening, the search for persistent signals and backgrounds. So far, we've talked mostly about discrete events, individual mergers. But gravitational wave astronomy has other listening modes. One is the search for a stochastic background, a random persistent gravitational wave signal made of many unresolved sources. It could be astrophysical, the combined hum of countless distant compact binaries. Or it could include something more exotic, a relic background from the early universe produced by processes like phase transitions, though that remains speculative and constrained. Another mode is the search for continuous waves, nearly monochromatic signals from spinning neutron stars with tiny asymmetries. If a neutron star is not perfectly symmetric, if it has a slight mountain, even microscopic, its rotation could emit gravitational waves continuously. These signals are expected to be extremely weak. They require long integration times and careful search pipelines. So, a long observing run can help, not because it provides a single loud chirp, but because it provides data volume and stability. There are also burst searches, looking for short gravitational wave transients that do not match compact binary templates. These could come from core collapse supernovae, cosmic string cusps, or other unmodeled phenomena. Most such searches so far have not produced confirmed detections, but they provide important constraints. Now, it's easy for this to sound like a list, so let's put it into a calm image. Imagine the gravitational wave sky like an ocean at night. The mergers are the individual splashes. The stochastic background, if present, is the steady surf. Continuous waves would be a far-off buoy ringing with a stable tone. Bursts would be unexpected, brief disturbances, rare and hard to interpret. In this analogy, O4 and future runs are about getting better microphones, quieter equipment, and longer listening times. And one of the most important scientific outcomes of longer runs is not just more events, it is better characterization of noise and systematics, understanding what the detector does when the universe is silent. Because only then can you be confident that a faint signal is astrophysical. This is why detector characterization, monitoring glitches, spectral lines, environmental couplings, is a major science effort of its own. It doesn't make headlines, but it is the foundation that makes the headlines trustworthy. Now, if you are still listening, here is an engagement question. Do you find the idea of a cosmic background hum soothing? Or does it make your mind more alert? Comment below. I can lean more into this meditative metaphor in future episodes if you enjoy it. In the next file, we'll talk about the rhythm of observing runs, why they pause, how upgrades change sensitivity, and what the next era may look like, without making strong claims beyond the public cautious picture. Let's continue. It's worth emphasizing that background does not mean boring. Backgrounds are often where the deepest cosmology hides. If we ever detect a primordial gravitational wave background, It would be a window into conditions far earlier than the cosmic microwave background can directly reveal. But for ground-based detectors, those early universe signals are strongly constrained and may be beyond reach, depending on the models. So, the honest stance is that it is a long shot at current sensitivities, but it is scientifically meaningful to search and to set limits. Astrophysical backgrounds are more plausible. The combined unresolved mergers too faint to pick out individually. As event rates increase and sensitivity improves, a background becomes a more relevant consideration. Now, continuous waves are almost the opposite of mergers. A merger is short and dramatic in waveform shape. A continuous wave is steady and patient. It demands long observation time, careful demodulation for Earth's motion, and computationally heavy searches across parameter space. If detected, a continuous wave could reveal a rotating neutron star's asymmetry, its ellipticity, and perhaps information about crustal physics and internal magnetic fields. But as of now, searches have produced upper limits rather than confirmed continuous wave detections. Upper limits still matter. They tell us how smooth neutron stars must be, or how small their asymmetries are. Now, burst searches are the realm of surprise. They look for coherent excess power across detectors without requiring a template. This allows sensitivity to unmodeled events, but it also increases vulnerability to glitches. So, burst claims require very careful scrutiny and multi-detector confirmation. In that sense, burst science is a test of both imagination and discipline. Now, if you want a sleep-friendly way to hold these modes in your mind, keep the ocean picture. Splashes, surf, buoys, and occasional distant thunder. The detectors are the microphones. The pipelines are the filters. The catalogs are the journals of what the ocean did tonight. Now, in the next file, we'll talk about the real-world timeline of O4, when it began, how long it ran, and why that length matters, using only cautious, publicly stated facts. Then we'll close with a clean separation between certainty and speculation. Observing runs are seasons. They begin, they pause, they end. And between them, engineers and scientists upgrade the instruments, reduce noise sources, and prepare for the next phase. This rhythm matters because sensitivity is everything. A small improvement in sensitivity means a large increase in the observable volume, and a larger volume means more events from farther away across more cosmic history. So why do runs pause? Because interferometers are not just built and then left alone. They are continuously improved. Mirrors may be refined. Lasers may be upgraded. Control systems may be tuned. Data quality tools evolve. Commissioning work reduces noise, and sometimes external events like earthquakes, storms, or local disturbances affect operations. In a calm way, you can think of it as tuning a musical instrument. You don't tune once, you tune again and again because precision drifts. Now, during 2004, public communications described it as the richest run of the advanced detector era so far, with roughly a few hundred candidate signals reported in real time. Those candidates will be turned into final catalogs through careful analysis and validation. And after 2004, the network enters an upgrade and commissioning period again, with schedules that can evolve as engineering realities and scientific goals adjust. So, the honest posture is, the future is planned but not guaranteed on a calendar. That is normal for frontier instruments. Now, what should listeners expect as the field continues? A few calm, non-sensational expectations. Better localization as the network improves and uptime increases. More detections of rarer categories as the search volume grows. Stronger population statements as catalogs expand. Gradually tighter tests of relativity as statistical power grows. Better chances of multi-messenger catches for neutron star events if localization and coordination improve. But we should also say what remains uncertain. How often neutron star mergers will be close enough for detailed tidal measurements? How frequently electromagnetic counterparts will be observable given viewing angles and jet physics? Whether a stochastic background will be detected with current ground-based detectors in the near term, or whether it will remain a longer-term goal. Whether any deviations from general relativity, if they exist, will be within reach of ground-based sensitivity or require future instruments. These uncertainties are not weaknesses, they are honest boundaries. Now, if you're still awake, here's a gentle engagement question. Do you like knowing the boundaries, what we don't know yet? Or do you prefer episodes that stay inside the safe zone of established results? Tell me in the comments. I can adjust how much uncertainty we discuss in future episodes. In the final file, we'll close with a clean summary. What is solid? What is still being refined? And what is openly speculative? Then we'll add a soft call to action and fade into silence again. Here is a simple public anchor for 2004. The fourth observing run, called 2004, began in late May 2023 and concluded in mid-November 2025 in the coordinated network. Public notices also described planned maintenance and commissioning breaks during the run, and schedule adjustments as the collaboration optimized performance. Later public statements marking the conclusion of 2004 described it as the richest observing run so far, with roughly about 250 candidate signals identified in real time during the run, and that these new candidates constituted a large fraction of the total gravitational wave signals observed to date by the network. Those are the broad, factual signposts, and they give you the scale of the era. Now, what does long run buy you? It buys time in band for continuous wave and background searches. It buys a larger sample for populations. It buys operational experience, learning how to run detectors more stably and how to reduce downtime. It buys better calibration practice, which improves parameter estimation. And it buys better coordination among observatories and telescopes. In other words, it buys maturity. Now, the network now enters an upgrade and commissioning period again. Public planning documents emphasize this rhythm: observing, then upgrading, then observing again. If you're a viewer, you might wonder, does this mean discovery slows down? Not exactly. Discovery changes form. It shifts from new detections every week to new understanding of what the detections mean as catalogs are refined and papers are written. So even when detectors are offline, the science continues. Now, one more integrity point, especially for YouTube. If a video says real leaked gravitational wave footage, that is misleading. Gravitational wave data products are not footage, and leaks are not a typical mode of scientific communication here. The honest framing is scientific visualization based on measured data, or CGI reenactment inspired by published findings. That framing protects viewer trust. Now we're ready to end. In the last file, we'll summarize what we know, what we're measuring more precisely now, and what we're still searching for. Then we'll let the night be quiet again. Let's end with a quiet, careful summary. What is solid? Gravitational waves exist, and ground-based interferometers can detect them routinely. Compact binaries, especially binary black holes, merge often enough that the gravitational wave sky is now a populated landscape, not an empty one. A long observing campaign can produce on the order of hundreds of candidate alerts, and over time, many become cataloged detections with measured parameters and uncertainties. What is still being refined? Population details, the precise shapes of mass and spin distributions, the mixture of formation channels, and the merger rate as a function of cosmic time. Multi-messenger coordination, how often neutron star events will be localized tightly enough, quickly enough, to catch light across the spectrum. Strong field tests, how tightly we can constrain subtle deviations from general relativity as catalogs grow. And what remains openly speculative? Early universe backgrounds detectable by ground-based interferometers, exotic sources that might appear in unmodeled burst searches. Any claim that a single event breaks known physics. Speculation can be beautiful, but only when labeled clearly. That is how we keep science calm and trustworthy. Now, if you enjoyed this sleep-friendly cosmic documentary, you can support the quiet universe in a simple, quiet way. You can like the video so it reaches more listeners who want calm science at night. You can subscribe so you don't miss the next episode. And if you know someone who relaxes best with gentle astronomy, you can share this with them. No urgency, just a soft invitation. Before we fade out, one final question. When you think of the universe, do you prefer to imagine it as light, stars and galaxies, or as vibration, waves moving through space-time? If you'd like, leave your answer in the comments. Now, let the idea settle. Imagine a distant merger, so far away that it is only a tiny ripple by the time it reaches us. Not a shock, not a blast, just a whisper. One slow breath in, one slow breath out. And as the night continues, the detectors keep listening, quietly, patiently, turning the fabric of space-time into a new kind of sky.
And if you want one last calm image, picture the Earth as a small platform, and on it, a set of long, silent arms of light. Above, the sky looks the same as it always did. Stars, darkness, distance. But beneath that familiar sky, the fabric of space-time itself carries information. It carries the echoes of mergers so far away that they are no longer loud events, only gentle ripples. When we say hundreds of signals, it is easy to imagine a crowded, noisy universe, but the reality is softer. Each signal is faint, each one arrives diluted by distance, and what makes them powerful is not volume, it is accumulation. 100 whispers can become one clear sentence. That sentence, so far, says, black holes merge often, neutron stars merge sometimes, and general relativity remains consistent with what we can measure within current uncertainties. It also says the universe is full of compact objects we cannot see directly in light, yet we can still study them. And it hints, as catalogs grow, we will refine our understanding of formation channels, rates, and rare categories. We may tighten tests of gravity. We may constrain nuclear matter more strongly. We may someday detect persistent backgrounds or continuous waves, but we will not force those outcomes with language. We will wait for evidence. That is the calm discipline of science. If you made it to the end, thank you for sharing this quiet time with the quiet universe. Like the video if it helped you relax. Subscribe if you want more calm cosmic documentaries, and share it if you know someone who likes to fall asleep to gentle science. And if you want to leave a comment, answer this. Do you feel the universe more as light or as vibration? Now let the thought fade. A last ripple passes. The instruments keep listening, and the night becomes simple again. And one last soft reminder of framing. The visuals you see in this series are artistic, scientific illustrations, AI CGI reenactments meant to help your imagination, not to imitate real camera footage.
With that clarity, you can relax into the ideas without worrying about what is literal. Just listen. If you're drifting towards sleep now, you don't have to remember details. Just keep the mood. A universe that can be heard, not only seen. That is enough. And when the next episode begins, we'll keep listening, slowly, one clear idea at a time. Until then, let the quiet do its work. Sleep well. The sky is still there, and the waves are still passing, even when we don't notice them. Good night.